Hello everyone, welcome to a problem session today. So today we have a problem in which we will balance energy coming in with energy going out, and then we'll come to a formula in which we can actually find the temperature of the moon based on how much the flux of energy that's coming in. So this is the what's given over here is a flux of energy that's incident on moon. Okay, so if you one way to analyze it, if the sun rays are coming in and maybe you have a moon here, so if you look at for all the rays that's going to be coming in, the one that will be within this area of cross section, so this will be absorbed, these rays will be absorbed. That means the energy here times the area of cross section will be tell me energy that's absorbed, and this is energy per unit time. So energy absorbed, we're going to say everything that hits gets absorbed. Okay, absorbed per unit time will be equal to this flux in, this is the flux in times pi, let's call it radius of the moon is r, this is moon, so radius of moon will be pi r square. So that's the rate at which energy will be absorbed. Then we'll say moon itself will be emitting radiation from the surface. So this is the surface of the moon, because it is at temperature T, is going to radiate out just like the sun. Surface of the sun has certain temperature, radiates out, so this is going to radiate out, and this guy has flux out. So that one is given by flux out is energy out per unit time over this time is going to come out on all this 4 pi r square. It's going to come out on 4 pi r square, and that this is equal to sigma t to the power 4. I'm just going to as a perfect black body. Okay, we just assume that, and sigma is the Stefan Boltzmann constant, which is given for answer given here. So this is one thing, and we can solve this for E out. How much energy is coming out of the entire moon per unit time is going to be 4 pi r square sigma t to the power 4. Okay, so this is second equation. This is based on energy coming out, and this is based on energy getting absorbed. Now we can assume that temperature has reached some kind of equilibrium, so energy coming in is equal to energy going out. So we can say that this thing must equal that thing. So this like a balancing energy in with out. So when I balance that, the right side should be equal to right side, and this value is given over there, and you can now you can see you can solve for t without even knowing the radius of the moon, right? So we can just make it 4 pi r square sigma t to the power 4 should equal to pi r square phi flux in. Of course, pi square got cancelled from both sides, so T is equal to pi in over 4 sigma 1/4. Now I can put the numbers in there. So the number is 1400 over 4 times 5.67 times 10 minus 8 to the power 1/4. Now we can plug into the calculator, and this is really 280 Kelvin. So this temperature, which turns out to be 7 degrees Celsius, 7 degrees Celsius, or 280 K is not, it's in the middle here, so it's kind of reasonable answer. Okay, you can see how broad assumptions we made, but we got a pretty reasonable answer. And this principle of balancing energy in with energy out if thermal equilibrium has reached is called energy balancing principle or detail balancing principle. So what we did was E in, so this is the rate at which energy was coming in and getting absorbed, was equal to E out. So this is the rate of energy was leaving. And so this led to the entire moon being at a steady state. This is a very important principle and solves a lot of problems with when you come right down to it, because you try to balance the energy in and energy out. Okay, this is kind of an important problem, and variations of this problem shows up in a lot of exams. Okay, so if you don't mind, you can subscribe if you like this kind of channels, this kind of discussion. And if you like this video, or please hit the like button. If you like me to do more problems, or I have some questions about this kind of problems, you can leave a comment and I'll try to address some of the comment. Thank you. Okay, bye.